Welcome all, and thank you for joining us today. My name is Hanan Moller, and I am a technical director with the application engineering team at Essent Embedded Analytics. In our talk today, we want to discuss in-life analytics. We will start by looking at the number of technology trends, all of which stand to benefit from in-life analytics. We will then provide a quick overview of the embedded analytics portfolio, hardware and software components, and see how those can help the system designer achieve some of their system goals. We start with a spotlight on 3 technology trends. The first technology trend I'd like to look at is autonomous vehicles. Self-driving cars is one of the hottest areas around. Competition is increasing amongst automakers to offer self-driving cars. Significant improvements to vehicle autonomy have recently been announced by various companies. Increasingly, car manufacturers are building their own SoCs, for example, Tesla's FSD, and developing much of the software needed for its autonomous cars in-house. High level of autonomy will bring vastly elevated amounts of sensor data and will require more performant CPUs in vehicle as processor workloads shift from detection-based control to predictive control based on artificial intelligence. Autonomous vehicles will not be detached islands of intelligence. Vehicles are becoming and must become increasingly connected. As car becomes more intelligent and more connected, the issue of their cybersecurity becomes ever more important. A security breach no longer endangers a single car. It can affect an entire fleet. One point I would like to bring out here is that as motor vehicles become more intelligent, more connected, and more sensor rich, the semiconductor content goes up. Self-driving cars are really becoming supercomputers on wheels with millions of lines of code. Processors and imaging devices support various levels of autonomous driving are entering the mainstream, and semiconductor content will only increase as cars move up the autonomy scale. This represents an opportunity for silicon vendors, but a challenge for designers keeping the increasingly complex systems running smoothly and securely. The next technology trend that we've witnessed over the last number of years is artificial intelligence and machine learning. Both of those continue to be part of this very significant trend, from insurance risk assessment, medical diagnosis, to self-driving cars. AI benefits from huge amounts of processing power, and for many years, much of the processing happened in the cloud. Sensors at the edge would collect and transmit most or all of their data to the cloud for processing. That gave access to an almost infinite array of low-cost compute resources to run AI algorithms, but was costly in terms of data bandwidth, suffered from poor latency, and the cost of the required infrastructure. AI edge processing today is focused on moving the inference part of the AI workflow to the device, keeping data local to it. There are different reasons why AI processing is moving to the edge device, which varies by application. Privacy, security, cost, latency, and bandwidth all need to be considered when evaluating cloud versus edge processing. Applications like autonomous driving, where an autonomous vehicle requires data to be immediately processed for tasks such as recognizing vehicles, recognizing traffic signs, pedestrians, and highways, have sub-millisecond latency requirements, while other like voice and speech recognition and smart speakers need to take privacy concerns into account. Keeping AI processing on the edge device circumvents privacy concerns while avoiding the bandwidth latency and some of the cost concerns of cloud computing. The third area is 5G. 5G is the fifth generation of mobile communication technologies. It's a follow-on of 4G, 3G, etc. Compared with previous cellular technologies, 5G aims to provide a far higher level of performance to support the growing consumer demand for mobile traffic data, but it also attempts to address a wider set of use cases and application. While the evolution of previous cellular generations had been mostly driven by technology advancements and the new capabilities they offered, 5G has been driven more by the need to provide ubiquitous connectivity to a diverse range of use cases and scenarios. ranging from data-intensive applications such as augmented reality or very high-definition video streaming to time-critical applications such as smart grid, automation, or the remote control of industrial processes. Let us now have a brief overview of the embedded analytics solution. Test and embedded analytics provide a system-wide hardware and software solution to help system designers achieve their analytics and monitoring goals. The light blue blocks here represent the main system of your SoC. You will have several processors, in some cases hundreds of them, accelerators, and many other types of IP. There is an interconnect or some NOC in there. Some of the IPs will have been purchased from third-party providers, and some will be developed in-house. The embedded analytics IP, a silicon IP portfolio, delivers three main functions: collecting and filtering data from the components and subsystem in the target SoC, transporting and transforming and transferring the data between the embedded analytics and the software layer, and responding in real time, if necessary, to critical events or system states within the SoC. Test embedded analytics has been designed and implemented as a scalable platform to harness complexity in SoCs and embedded systems. The silicon IP portfolio comprises of more than 30 IP products delivered as synthesizable Verilog and is silicon proven in a wide range of process technologies down to 7 nanometers and clock speeds of up to 3 gigahertz. The software interface is a layer of services facilitating communication with the embedded analytics IP subsystem and enabling all key functions such as IP configuration, data retrieval, and, where appropriate, interaction with the SoC to take place. Some of those interaction examples include CPU debug and run control. These services, all those software services can run on the host with a physical connection to the target SoC or over a remote connection to a host running in a remote site, whether it's over Ethernet or a wireless connection. The embedded SDK, which has recently been introduced, simplifies the creation of a self-contained monitoring and analytics environment on chip. It consists of a set of APIs that open up access to the full functionality of the Tessent embedded analytics IP. The Tessent embedded SDK is a set of software libraries and APIs. It provides a way to configure and control embedded analytics monitors from within the SoC itself and process the resulting system-level behavioral data in an application layer running on a CPU within the SoC. The system designers can create custom applications using the data collected by the Tessent embedded analytics IP. The embedded SDK abstracts the implementation details and allows for efficient interaction of the application with the hardware. Tessent's IP brings system-level visibility into the operation and status of the SoC into which it's being deployed. The embedded SDK facilitates the implementation of an autonomous mechanism to continue running and managing the analytics subsystem, providing a way to configure, control, and process data from the embedded analytics IP, with no need to connect to an external software utility or remote host. While this is often useful during SoC bring-up, it is invaluable when deployed into a final product where an external connection to the SoC is simply not available. It allows an entirely on-chip configuration and analysis solution that can independently be configured and manage the analytics IP. Information obtained and processed via the embedded SDK can be used to make decisions locally. For example, in self-driving autonomous vehicles applications, embedded SDK libraries can be included in code running on the SoC to warn the system of anomalous conditions across the onboard ECUs and let the main CPU decide what course of action to take. Alternatively, system and status data can be captured and processed and then either actioned, discarded, or recorded for later download and offline processing. So what use cases are there? Where do we need to use embedded in-life embedded analytics? So embedded analytics is being used both in lab and in life. The more traditional in-lab use cases focus on debug and bring up. So we're trying to find bugs, finish our bring up, optimize our firmware, and basically get to market quicker. The need for in-life embedded analytics for using it whilst deploying in the product is driven by different requirements. For example, safety and security, regulatory reasons, and performance optimization. Let's now look at some of those cases in a little bit more detail. Safety and security requirements may require a system to take immediate action to mitigate dynamic risks. This may require timely detection of potential risks and immediate reaction to mitigate those. Cybersecurity of vehicles is no longer an issue for automakers to address as they please. It has now become subject of regulation. For example, the UN Economic Commission for Europe formally adopted new regulations on automotive cybersecurity. One of these, the new WP29, is being driven by the increased intelligence of vehicles and the connectivity amongst them. As part of the new regulations, OEM will need to prove that their cybersecurity management systems and processes effectively deal with the identification, characterization, and remediation of threats throughout the life cycle of the vehicle. Performance optimization can now take into account the dynamic behavior of the system. With a rich set of data being collected from the relevant sources in the system, the embedded supervisory software can self-tune and adapt to changing conditions. There is also the opportunity to feed the data back as additional training data in ML-based scenarios. Let's look at a little bit more detail in some more specific use cases. In the context of autonomous safety, an EDA supplier needs to ensure maximum safety in vehicle. One aspect of this involves maintaining the integrity of the images received from onboard cameras. Embedded Analytics IP can monitor and trace bus activity on the SoC, filtering on camera data. Individual frames are reconstructed from the camera data as it is being written to memory, so that differences between the current and previous frames can be evaluated. Images that do not change from frame to frame can be detected, whether in part or a whole. This could be, those differences can be due to malicious interference, camera malfunction, sensor malfunction, or obstruction of camera view. System software will be notified about those stuck or unchanging regions and then take an intelligent decision based on other state conditions of the car and take the appropriate course of action. The second use case we will cover is AI at the edge with cloud-based. The tasks involved with self-driving a vehicle will continue to be delegated to edge AI, taking advantage of the lower latencies in the system. However, there are scenarios where a combination of edge and cloud do bring benefits. In such hybrid scenarios, AI is driving the car, but it is also monitoring and safeguarding the entire fleet. The electronic control units within each car will have been instrumented with embedded analytics together with the embedded SDK. Status information is uploaded to an AI-based central intelligence in the cloud, either in real time or periodically. The central intelligence can fulfill a number of key functions of great interest to a fleet operator. At the simplest level, it can track and report the driving hours of every vehicle in the fleet. It can detect and react to emerging threats such as coordinated cyber attacks. The off-board compute systems can allow data to be analyzed in real time across the fleet, allowing detection of conditions outside of the design limits on individual vehicles and across the entire fleet. The aggregation of data at fleet level can help detect gradual performance degradations, for example, degradation of electric vehicle ranges, or manufacturer defects which would not be detectable at the individual device or vehicle level. Effective detection of emerging threats or possible systemic defects allow the fleet operator to quickly begin to deploy countermeasures or mitigation plans. In a 5G base station SoC scenario, consider a case where a 5G network provider wants to track its network performance against different SLAs. One device may need to support multiple SLAs concurrently and will have to detect and, where possible, mitigate delays to data packets. This can be achieved using embedded analytics IP, embedded SDK, and a runtime analytics application. One of the CPUs in the system runs the analytics application, interacting with the embedded analytics IP. System software and hardware IP use the static instrumentation IP to record and collect instrumentation, information that a particular software or hardware task performed operation X at time Y. This information can be used to then reconstruct the sequence of task completions, control flow with order and timing. The static instrumentation module is used by software operating within the embedded SDK and by the hardware accelerators to give an indication of how the system is performing. The tasks that need to be carried out are known, of course, at compile time with the timing, maximum timing limits and their order. This information is embedded into the analytics software to monitor and verify that the predicted program flow, together with its associated timing information, is indeed observed during the real-time, during the operation of the system. If the program executes as predicted and within the permissible time bounds, then all is well. If it does not, then there may be a problem, and the analytics CPU will cross-check with status information from other analytics modules, such as the bus monitor, status monitors, etc., to get more information about the state of the system when the error was happening. If the analytics CPU concludes that an error condition is real, it will report as such to the system CPU together with the details of what the error was. The embedded analytics IP, together with embedded SDK, help to affect an embedded system which can detect and recover from many kinds of errors, and it's entirely independent of the system hosting it. This is a powerful capability for carriers, manufacturers, and users of 5G new radio. In summary, embedded analytics IP and the embedded SDK offer chip designers a way to implement and implant intelligent self-analytics in their devices throughout the IC lifecycle, from lab, bring up to in life. It marks a fundamental shift of analytics insights from the lab to the final deployed product, with the embedded SDK enhancing the value of any device into which it's being deployed. The data gathered from onboard analytics will enable a whole new class of applications, bringing value to the designer, the manufacturer, and ultimately the user. Meanwhile, the decisions taken by application code running on top of the embedded SDK based on such data will mitigate against errors, anomalies, and cyber attacks, protecting the system around it and potentially saving lives. Thank you very much. I hope you have enjoyed the presentation. And if you have any questions, please don't hesitate to stay after the talk. There is going to be a Q&A session, or contact us directly in the email that you see on your screen. Thank you very much for your time.